So we defined operator L, and we said that L has a linear transformation, okay, from tangent bundle to another tangent bundle. Okay. For some reasons, and we'll see the reasons I'm defining a bilinear form, okay, that is torsion, okay, of the connection. So I'm defining torsion of connection. So it's just a symbol. We'll talk later about it. That is what does this mean? You can find it at the end of the notes actually. What is the physical meaning of this kind of a torsion? But it's a quantity that you define in this manner. So the torsion takes as an input two tangent vectors and gives you as an output the covariant derivative of x with respect to y minus the covariant derivative of y with respect to x and minus the commutator x1. Okay? So the torsion is a quantity. So we have this operator. So what we say that the torsion of a pair of tangent vectors is the covariant derivative of y with respect to x and the covariant derivative of x with respect to y minus the commutator. I'm going to say a connection delta x maybe is a torsion free. Torsion free if what happens? If the t of xy is a 0. Okay? That is, that if you take this difference of the covariant derivative of x with y and y with x, this is equal to the commutator or the Lie bracket of x and y. You're going to call it a connection torsion free if this torsion of the connection is identically 0. Okay? With this notion, I'm going to prove a result which is going to tell you a new piece of information about L. And they say that L is a self-adjoint operator. Okay? So in other words, this shape operator is a self-adjoint operator. Okay? How can I show L is a self-adjoint operator? There will be consequences of L being a self-adjoint operator. So in order to show L being self-adjoint operator, I need to show that y is same as x and y for all x and y. So it satisfies this identity. Okay? That was something that we during function analysis. If you haven't done function analysis, fine. In other words, an operator is self-adjoint if you can, kind of shift this L onto any other side of, the inner product without changing it. Okay. How can I prove it? How can I prove L to be a self-adjoint operator? So let's have a look. So let's compute the difference. The inner product of Lxy minus x interested in proving that this must be 0. Okay? So this is what I would like to want. By definition, this will be minus the covariant derivative of x, covariant derivative of the normal vector in the direction of x in a product with y, plus the x with the covariant derivative of x with the inner product y.
With respect to y, sir.
With respect to
Y.
Ah, yes, okay, so this must be plus a. Okay.
Derivative, sir. The covariant derivative, it should be with respect to y because it's L of y.
Ah, okay, yes, yes. And I'm going to have a minus here, and this will be minus.
Minus.
I can put a plus afterwards. You get it. Observing that since x and y are the tangent vectors, so I want to talk something sensible about this expression. So observing that x and n and y and n are what? They are orthogonal to each other. So x and y are tangent vectors, n is a normal vector field, so they both must be equal to 0. Okay? And assuming the compatibility of the metric, let's compute the covariant derivative of this and this quantity. So what would be the covariant derivative of this quantity? Del x of xn would be, so obviously this is going to be equal to 0 for sure. And if I assume the compatibility of metric, I'm going to get del x. I must put a y here. अगर x का कर रहा हूँ तो with respect to y करना चाहिए, this must be better. So del y x n plus
x times x in the product
x
x
in the product
del y operated
del y operated on and actually n equal to 0. Okay? And if I take this on the other side, so what does this shows is that del y x n is equal to x. Can I say this would be same as del y n actually? Okay? Okay. So because I kind of computed the expression for this, and what does this show is that I can, if I wish, I can shift this operator on the other side as well. So I can get it. And similarly, I can show that if you have minus del xn in the product with y, so this must be same as n and del xy. Agree? We're going to have something like that. So now I'm saying that let's take these two quantities and substitute it here, and let's see what you get. Okay. So we get Lx y minus x Ly equal to, so the first is going to be n del x y minus, the other quantity is
x minus the
n del yx actually.
yes
Okay.
sir.
And since the inner product is commutative, I can also put it in this manner. So n del yx Agree? This will be the case. And then by properties of inner product, I can combine these guys. Okay? So it's going to be del x y minus del y x. Okay? And now, what is this quantity? So that's a commutator acting. Okay? But we proved
So only if torsion is free, and it's torsion free.
if the delta x is torsion free. Let's keep it on hold in the sense that let's assume that delta is for now torsion free, and let's see explicitly that why it is torsion free. Now there are lots and lots and lots of remarks. What is the first theorem that you remember about the self-adjoint operators from your function analysis course? Any theorem? So if an operator is self-adjoint, then all eigenvalues are real actually. Okay? All eigenvalues must be real. That's the first thing that we proved. Then we proved that if you take any two eigenvalues which are different from each other and you take their corresponding eigenvectors, they must be orthogonal to each other. This is also, we proved actually that if you take two vectors which are eigenvectors corresponding to two eigenvalues, then they must be orthogonal to each other. Okay? Maybe you can recall this result. So this is one of the case. And the second thing that we must say. So here's the thing. If I want to write a matrix for L, what would be the dimension of the matrix for L? So L is mapping what to what? So it's mapping a tangent space to tangent space. And what is the dimension of tangent space? It's a surface actually. It's a two-dimensional thing. Surface is a two-dimensional. Plane is a two-dimensional thing. So tangent space is like a plane actually. Okay. Do I need to convince you that plane is a two-dimensional thing?
No, sir, the surface is two-dimensional.
Surface has two dimensions. You need only two quantities to express any point on the plane. Okay. The plane.
Plane is a specific case of the
Surface. So we know that the surface is a two-dimensional. So plane is a two-dimensional thing actually. Okay. So L has a dimension that is a vector space of dimension 2, and the codomain is also is a vector space of dimension 2. So what is the dimension of matrix 2? So it's a 2 by 2 matrix. L is a, the first remark is that since L is a map from tangent bundle to tangent bundle, so the matrix representation of L is a 2 by 2 matrix.
in 2 by 2 by
I'm sorry?
yes.
So it must be 2 by 2 matrix.
2 by 2
ठीक है. For this 2 by 2 matrix, how many would be their eigenvalues actually?
Maximum.
Maximum 2. Maximum 2. So the consequence of this is that L is going to have two eigenvalues. Okay? Let us denote those eigenvalues by kappa 1 and kappa 2. And eigenvectors. Eigenvectors, let's call them x1 and x2. Okay, it's going to have at least 2 eigenvalues, maybe at most 2 eigenvalues and 2 eigenvectors actually. These eigenvalues, k1, k2, are called the principal curvature. What do you mean by that? We can show that these are k1 and k2 are the maximum and the minimum values of the normal curvature. And these vectors x1 and x2 are the principal directions. Okay, so in other words, these are the directions in which the curvature, the curve is going to have maximum or the minimum, what do you call, curve actually. So if I set, for example, k1 for the maximum curvature and k2 for the maximum minimum curvature, then x1 and x2 is going to have, what do you call, x1 is the direction of the maximal normal curvature, and x2 is the direction of the minimal normal curvature. And how can I understand this curvature? Okay, so if I, for example, okay, take a cylinder, okay, a plane is easy actually. The trouble with the plane is that in both directions the curvature is 0. Okay, even in the case of the cylinder, okay, in case of the cylinder you will have two different things actually. Okay. So this is one principal direction, okay, and that's another, what do you call, principal curves actually. So it's going to have a 0 curvature here, because if you draw a normal vector, it's not going to change anything, any of its direction actually. Okay. So it's going to have a 0 curvature, and while this guy is going to have a positive curvature actually. So that's k1 and that's k2. Okay, so going in this direction is the principal direction anywhere you like, and going in this direction is the principal direction before. Is it making sense? And similarly, you can talk about sphere.
So in the case of this cylinder, the curvature will be 0 or negative?
0. It can't be negative. So
the direction of the curve.
Okay, so there is no part of the surface which is something like this actually. I'm sorry? But the normals are always outward actually. They can't be inward. That's what the definition of the normal is. Okay, the normal is what? So we say that surface is a kind of a space on which you can always draw outward normals actually. Okay? So if you are on a saddle, then even in that curvy part actually, the normals are outward. So it's not going inside the surface actually. You are getting the point. Okay? The normals are outward. So one direction going to have k1 positive, another direction is going to have. Is it making sense? So in other words, every surface, every specific surface has a shape operator associated with it. And if you know the matrix of the shape operator, you can fetch all information about that surface out of it. Are you getting the point? Let's do a little bit more. So see, computations are not difficult, right? And the key thing is that we must be able to make sense of this basic theory. Must be able to convince ourselves that what we are talking about is this basic. So now I would like to talk about the different cases of K1 and K2 By the way, what would be the determinant of this matrix? Determinant of this L. How does the matrix would look like explicitly if I want to write it? So it's going to be something like this, since it is diagonalizable. K1, K2 and 0, 0. So this would, that's how the matrix would look like. Okay? So the determinant of L would be K1, K2. And this is what do you call the Gaussian curvature. So the Gaussian curvature can also be determined through the operator. Okay? So even the Gaussian curvature is sitting in this operator. How about if I take the trace of the matrix cell?
K1 plus K2.
So it will be K1 plus K2. The mean curvature would be if I multiply it 1/2. Okay? So this would be half, and you're going to have an edge curvature. So this would be what you call your mean curvature. Is it making sense? What we are going to see afterwards, okay, mean curvature is an important quantity because if it tells you that, okay, so if the mean curvature of some surface is 0, that surface is something called the minimal surface actually. And what do you mean by the minimal surface? So in other words, okay, have you seen something that want to kind of shrink its surface actually, somehow? Have you seen something like that? Okay, take any cross section and make a soap bubble out of it. Soap bubble, think about it. So usually हम क्या करते हैं? So we take a circle, okay, circular disc, and you make it and then okay, you get a bubbles out of it actually. Okay, so these bubbles, and even the surface that is basically inside the soap film that you have inside that circular ring, that's a minimal surface actually. That's a minimal surface. Okay. So you can make so any surface that you can make out of, for example, this soap stuff actually, soap bubble, so that would be a minimal surface. So you can take any other cross section. I can take a rectangle, I can take a disc, I can take a tilted ellipse, I can take any kind of thing. So it's like if I dip it, I'm gonna get a surface actually. Okay. So it's a kind of a surface which has a tendency to push itself or shrink itself actually. Okay, it don't want to expand. Okay, it just want to become a stable actually. So you call that as a minimal surface. So any surface that has a mean curvature 0, it's a minimal surface. Okay, soap films. And this is of very, very importance. Even the lady, this lady who has got this field prize this time, the old lady. So her work is on minimal surfaces. She kind of gave a completely new way to discuss these